Muy buenos días a todos. Es un placer estar con ustedes en el marco de Tijuana Innovadora 2020. Tijuana es el futuro en temas de salud. Quiero presentar este día a ustedes uno de los personajes más extraordinarios, destacado y relevante en la medicina de nuestra era y de todos los tiempos. Médico cardiólogo, intervencionista, científico, inventor, a quien se le ha otorgado la presea más importante, equiparable al premio Nobel, pero en la bioingeniería. El Fritz J. and Dolores Russ Prize, premio internacional, otorgado en enero del 2019 al doctor Richard Schatz por el invento, desarrollo, innovación de la tecnología del stent, el Palmaz-Schatz stent, que recibió compartido junto con el inventor del stent periférico, el doctor Julio Palmaz. Tecnología que se ha adoptado en el mundo entero y ha provocado el avance del intervencionismo percutáneo mínimo invasivo para destapar y desbloquear todas las arterias del corazón y los vasos. Por eso se ha considerado que esta tecnología es una de las aportaciones más grandes en la historia de la medicina. Como ustedes bien saben, el infarto agudo de miocardio es la causa número 1 de mortalidad en los adultos y tan solo el año pasado aproximadamente 18 millones de personas fallecieron a causa del infarto de miocardio. El 85% de ellos, por lo menos, fueron un infarto al corazón. Por lo tanto, el stent, y gracias a ello, millones y millones de personas han salvado sus vidas. Se considera el invento más grande que ha surgido en la humanidad en los últimos años. Con ustedes tengo el gusto de tener con nosotros, a distancia por la pandemia, pero pronto lo tendremos con nosotros, presentarles al doctor Richard Schatz, director de Intervenciones e Investigación Cardiovascular de Scripps Health y Presby's Heart Center de La Joya, California. Es un honor para mí y ha sido muy afortunada, ya que fui su primera discípula en los Estados Unidos en intervencionismo avanzado. Con esto dejamos una gran amistad que hemos cultivado por años. Además, seguimos colaborando juntos en varios proyectos y en los principios del año el doctor Schatz expresó su deseo de venir a Tijuana a colaborar y trabajar con nosotros en el Instituto de Ciencias Cardiovasculares para seguir investigaciones y avance de la tecnología invasiva. Muchas gracias, Richard. Thank you so much, Richard, for being here with us in Tijuana Innovadora 2020. Thank you. I know your busy schedule, and nobody better than you to tell us about this beautiful success story about you and the Palmaz-Schatz stent and its evolution. Thank you, Richard.
Thank you very much, Pat, and it's a real pleasure to be here with you. And for those, I think you did mention it, I do understand a little bit of Spanish, but Patricia was our premier interventional fellow many, many years ago, the first, and it was always a pleasure to revisit with her and to see how successful she has become. Well, this is a fun story. We're going to try and keep this around 30 to 40 minutes. And it's a fascinating story at many levels, but I think the probably most interesting thing is it's a story that never should have happened. There were so many errors and so many things that happened along the way and barriers that it's nothing short of a miracle that we were able to put this together, because we quite honestly didn't know what we were doing early on, and we had to make it up as we were going along. So that's what this story is all about, and the backstory about how we nearly failed more than once. So if you ask in a room of people, raise your hand if you have a stent or know anybody who's had a stent. And of course, all the hands go up in the room, and that speaks to the ubiquity of the procedure and how universally acceptable it's become, and quite honestly, how easy it's become compared to the old days. We take so much for granted when we put a stent in, but Patricia will tell you, since she was there from the beginning, that it wasn't always that way. And that's what I want to talk about today, is give you an appreciation for how things have changed and what it took to really go from just a simple idea on a piece of paper to a product that you can actually put in humans. So even though we were very successful in the end, it wasn't always like that. And for many reasons. Back in the early 1980s, after I met Julio, and I met Julio in 1985, and the day I met him and I shook hands with him, my life changed forever, and it set into motion a whole series of events that ended up changing the world in ways that we never could have predicted. But it didn't really start that way, because we got absolutely no encouragement from all of the experts and all the pundits. This is just a sampling of some of the probably dozen companies that I went to try and explain what we were trying to do and actually try and get support for continuing our research. And we were rebuffed at every point. And these were the experts at the time, of course, in cardiovascular innovation. And it was always the same story: it'll never work. And these are the reasons why they said you can't do this: clotting, infection, edge dissections, restenosis, rupture, erosions, aneurysms. So what's interesting is that we basically didn't listen to them. We decided that they were wrong and we were right. And it didn't end there. When we took this to Europe, after we did our first few cases, we got rebuffed again by the experts there. Dr. Schatz, you should be ashamed of yourself. It's unethical to put metal in human coronaries. And further in Europe, we didn't get much support. Here are some quotes from the European Society of Cardiology meetings. There's no future for stents. Here are all the companies that weren't interested. We actually, Julio never filed patents until I met him, and then we filed the patents. And we tried to give those patents away for free in exchange for just research time or some minimal support. And USCI, Cook, UT San Antonio, the VA system, we asked them all for support. In exchange, we would give them the patents, and they were refused. And then we finally went to the biggest player in town. That was ACS, Advanced Cardiovascular Systems. Eventually, this became Guidant. And they said it wouldn't work either in '86. So with all that, we went off on our own, and we finally met Johnson & Johnson and Boston Scientific. Boston was very interested, but they didn't really have the resources to do a project like this. And 1986, Johnson should get a ton of credit, because they were the first ones with the vision and also the willingness to take the risk. So they get a lot of credit for being innovative and also for having some vision. So how do we go from all that to one of the top 10 medical inventions of this century? We've been in IP worldwide twice, I think, and then there they said this was the patent that changed the world. We almost eliminated bypass surgery. Some of you are probably too young to know, but in the 1970s and 80s, everybody got bypassed. We did hundreds of thousands of these every year, and that's been reduced drastically as stents have become better and better. And then finally, when we went to Johnson & Johnson, the vision of this one person, Mike Schuler, really was the one that was driving everything. And he said this right after the very first presentation that I made to him. And he said, the body is just a series of tubes waiting to be stented. And he was right. So in a snapshot, let's see what's happened from 1978, when Julio had his very first idea about putting metal in the coronaries, to the current 2020. And this date's important, 1978, because there were so many copycats and suitors who came along and said that they really were the inventors. It was their idea. But Julio really was at least 8 years ahead of our closest competitors in terms of innovation and actually doing the hard and heavy lifting. So he should get a lot of credit for that. So in this period of time, millions of patients have been treated, probably 100 million or more. STEMI mortality has been greatly reduced. Bypass surgery is almost eliminated. And we can treat people that we never dreamed of with the balloon. And when balloon angioplasty came out, we were only doing very, very simple lesions, type A lesions for the most part. When Hartzell came around, he started tackling more complicated vessels, but the results really were pretty bad. They weren't very good. But we do vein grafts now. We weren't doing those back then. We couldn't do bifurcations. The equipment wasn't suitable. We can do STEMI patients. That was unheard of back then. We can do almost any vessel down to 2 millimeters now. And we can handle calcified vessels thrombotic vessels and tortuous vessels. They're hard, but we can do them because the products have gotten better and better. And don't forget, aside from just the coronary applications of the stent, modifications of our design have been used now extensively in other disciplines. The TAVR market is only possible due to the Palmaz stent. And if you look at it carefully, the fundamental cage that's used, except for the self-expanding stent, of course, is a Palmaz stent. And that's an idea that we actually came up with in the 1980s as well. We just never followed up on it. You'll see later in the history part of the talk. Other applications that you can't forget about is the aortic bypass grafts. These are all modifications of the Palmaz design, of course, all the pediatric applications. So the spin-offs from the basic stent design are actually pretty extraordinary. And even though even today in 2020, we hear about, oh, we put too many stents and stents don't really work. If you look at the press, you'll see a lot of, every time a study comes out, like the ischemia trial or orbit trial, you'll get a whole flurry of activity from the press. Oh, stents don't work, stents don't work. Well, they work just fine, right? And there's one place that's undisputed, and that's the treatment of ST elevation MI. So in 1973, when I saw my very first heart attack patient, the mortality was 20 to 30%. Treatment was 4 to 8 weeks in the hospital of bed rest. Medications were Lasix, oxygen, digoxin, aminophylline, and morphine for heart failure, and that was it. And angiography was forbidden. We had angiography in the 70s. We just did it in a very limited fashion. So you fast forward to the modern day, now we have a 3 to 5% in-hospital mortality, 2 days in the hospital. We have all kinds of medications. Of course, everybody gets an angiogram and everybody gets a stent. So that would not have been possible were it not for the stent, and that's indisputed. And here's a quick example of that. It's one of my favorite cases, a case that I did a few years ago. And this is a very young man, 39-year-old man with a STEMI. This is something we never could have done years ago. And right here, you see the stump of the fresh occlusion of the LAD before and after stenting. And that's not really what made this guy interesting, because his youth, really, we were surprised to find he had a total right occlusion that was chronic, and that was stented. You can see the nice result there. He had a total occlusion of his circumflex, and that was stented successfully. He had a total occlusion of what started out and looked like a very small ramus, but when we got done with it, you can see how large it was. And we did this total revascularization because we were directed by his MRI and viability, which showed that the entire ventricle was viable except for the inferior base. So although it was aggressive, I think it helped him. And in fact, his ejection fraction did improve. So there's a lot of stories about the old days and what happened in the stent evolution. But here are some of the secrets that really nobody knew. And that is that Julio never felt that his invention was worth filing a patent. He did not consider it an invention. He just considered it a research project. So when I met him, he had been working on it for 7 years and never once thought of filing a patent. And thankfully, he didn't make any presentations earlier, but he did make one on November 7th, 1984 at the RSNA. And that's where he showed, for the very first time, as a public disclosure, he showed the initial data of the stent. And what he didn't know, though, was that, and I hadn't met him yet, so what he didn't know was that the clock starts ticking. And once you make a presentation, you have 1 year to file your patent, or else it becomes public domain. We also lost all of our international rights by that presentation. But we did get the patent submitted just in time, exactly 1 year later, and that allowed us to protect the idea. The other thing that most people don't know is the FDA was very disorganized back then. The FDA did not believe in randomized trials. So they actually forbade us from doing one. We wanted to do a randomized trial. That was my idea. And they said, no, you don't need to do one. We begged and begged. They said no. And of course, that sounds crazy, but that's the way things were back then. They also wanted us to do the peripheral study first, the PAD study first. And they didn't ask anybody else to do that. So all the other stents that followed did not have to do that. So we had to do the iliac trial, and that paved the way for everybody else. By the way, when we did our first randomized trial, the FDA stopped us from doing it for a bunch of reasons, but we were trying to sneak it under the table. We did our own randomized trial, and they got really mad at us, and they made us stop. And some of the things that along the way that I didn't plan on, the early complications, the difficulty trying to get people to follow the protocol. Even when the stent was approved, the J&J wasn't ready for the demand, and we had a lot of supply issues, and we couldn't supply all of our customers, which was disappointing. we didn't plan on such vigorous competition. By 1998, we were knocked out of the box by the multi-link stent, or the Xience, eventually the Xience stent. And we went from 100% market share to 5 or 10%. We found it very difficult to change the design, even though we had great ideas. Corporations are very, very difficult to work with when you want to change things. Once they have something, they want to stick with it. And the FDA was driving us crazy because they would tell us one thing one day and something the next day. So in 1985, a lot of things happened. Here's Charles Dodd, the father of all intervention. They used to call him Crazy Charlie, but look when he died in 1985. And of course, Mason Sones, he died in 1985, the granddaddy of all angiography and cardiac angiography. Melvin Judkins died in 1985, and Gruncic died in 1985. So hard to believe that all of our mentors and giants all died in 1 year. Gruncic, of course, was the swashbuckling Swiss cardiologist, radiologist, vasculologist. And here's his kitchen table with his assistants where he did all of his work. This looks a lot like how Julio started. And here's a very famous picture of him presenting his data in 1976. This was the very, very first time the world saw what the balloon was doing. And these are balloons that he made himself, very reminiscent of what Julio was doing. Julio made everything himself in his kitchen. And Gruncic was the same. Very important picture. Ironically, I was at the American Heart meeting in 1976, and I'm sure I walked past this poster and didn't even notice it. I'm going to skip that for now. The very first angioplasty was done in Zurich by Gruncic and Bernie Meyer in September 1977, and this patient is still around, and here's his anatomy. You can see a proximal LED lesion, and that lesion was ballooned and thankfully stayed open for a long, long time, and led the way for Gruncic to start all of his initial trials, and up until the time of his death as well. So these are the three big pioneers in our world. And Charles Dotter, of course, was the radiologist, then Gruncic with the balloon, and then Julio Palmaz with the concept of a balloon expandable stent. There's some other mentors out there you should know about. John Simpson, of course, he started the ACS company that led to the multi-link stent. And then, of course, Paul Yock. Richard Stack doesn't get a lot of credit, but he came up with the bioabsorbable stent. And he came up with that, believe it or not, in 1985, 86. Right about the same time that we were doing our work, but he never published anything on it, and he kept it very secret for a long time. So 1985 is very, very important for the simple reason that angioplasty had been around now for 7 or 8 years. Gruncic was doing courses every year, but we had to live with an acute closure rate of about 10%. Acute closure was defined as closing of the vessel within 24 hours, and it might even have been higher than that. That's the number that we all sort of promoted, and it was probably generous. There was a separate problem of subacute closure, but it was extremely rare. I only mention that because it's the exact opposite of what we have now. Stents eliminated acute closure, but we substituted subacute closure for it in the early days of 3 to 4%. The restenosis rate, we don't really know what it was because there was no quantitative assessment back then, and everything was done visually. So if you looked at an angiogram and then decided to quantitate it, you just looked at it and said, well, I think that's 50%. But we don't really know what the number was. It might have been higher than 50%. But keep in mind, that was when we were doing simple lesions. So we did not do chronic total occlusions, acute infarcts, multivessel disease, vein grafts, bifurcations, calcified vessels, long lesions. These are all discouraged. So it was a very limited field that people we were taking care of. And as a result of that, the surgeons started coming out publicly and saying that the data stinks and we think you're wasting your time. No one should get balloons anymore. So a real battle was raging around 1985. And I remember this going to the meetings, and the surgeons were very, very, very vocal about this. And there were a lot of debates, and it was very hard to argue with them because the results we kept thinking were great, and they were great when it worked, but when it didn't work, they ended up with bypass. So something had to change. So the stent came around at a very good time. And here's a true quote from a surgeon: remodeling your artery with angioplasty is like remodeling your living room with dynamite. So Gruncic was a real showman. He put on these courses every year. And at the end of the course, he always wanted to have a big family picture. If you look closely, that's me right there. And this is 1985. Why this is important, and here's Gruncic right there. And there's Simon Sturzer right there. A lot of famous people here. Here's Joe Brown. And look at the date here. Why this is important is that I had contacted Gruncic to meet with him to actually show him our data. We had permission from our lawyers to actually show the data to Gruncic. because we filed our patents. We're about to file them, so they were satisfied we do a private disclosure. He was very excited about it. I got to set up a time, and we had it set up for October. And the weekend that I was supposed to fly out there is the weekend that he died in his plane crash. So we never got to show him all of our data, which is really sad, because I think he would have really appreciated all of our work. Here's a picture of a young Dr. Palmaz holding up the stent. Just a little bit about him. He was born in La Plata, Argentina, and sadly his father died of a STEMI when Julio was very young. His dad was about 50, and Julio was about 12 or 13. And also, a curious thing is that his father-in-law also died of coronary disease during a bypass by Favaloro himself down in Argentina, which is really also very sad. So Julio went on to medical school in Argentina, but he knew he wanted to come to America. So by 1977, he ended up in Martinez VA, California, in San Francisco, basically. Keep those dates in mind. He saw Gruncic in 1978, and this is where he had his first stent concept. And by 1981, he moved to San Antonio, Texas with his mentor. And between this time, he built many prototypes, did countless animal studies, but he had absolutely no plans for human use. This was just an interesting project. I happened to meet him in 1985 just by serendipity. My story is not quite as interesting, but I was in San Francisco the exact same time he was then. I moved to San Antonio, of all things, the exact same time he did. And I met him just by a fortuitous introduction. And after that, the rest was history. When I met him, I looked at all of his work, and I just said, we're definitely going to do this. And he said, no. I said, no, we can do this. It's going to work. He had shown me so much data that I thought it was unimpeachable information that we knew we could get it to work. He only worked in the big vessel, so my job was to make it work in the small vessel. So we take a lot for granted, but we put a lot of work into trying to figure out how to do that safely. So right about this time, how it all started, I happened to be at the Brooke Army Medical Center in San Antonio, Texas. And in 1982, I finished my fellowship and I was promoted to major, and I was supposed to be sent back to San Francisco where I started. But I begged my chief to keep me in San Antonio because I just married my wife and she just started dental school and we didn't want to split up. And so he reluctantly let me stay. And had he made me go back there, I never would have met Julio. So I probably wouldn't be here today. So right down the street from the Brooke Army Medical Center is this research place. And they have a colony of baboons there that had been on high cholesterol diets for many years. And I was just looking for a research project, something to keep me busy. I wasn't attending at the time and had some time on my hands. So I went over there and they had a cath lab of all things, a beautiful cath lab that somebody paid for, but there was nobody there to do anything with the animals. So I spent the next year just cathing all the baboons and trying to figure out what happens to their coronaries. And I just happened to meet Julio there one day. So after I meet Julio, then we strike up our little partnership, and then we decide that we need some money because we'd run out of money. And remember, I told you that nobody would give us any money, and we couldn't even give the patents away for free. So I'm on the golf course one day, and I meet this fellow, Phil Romano. He's a very popular, bigger-than-life figure in San Antonio. And he likes the story, and he says he wants to put a deal together where we can all work together. So we started a company with these three guys, and Phil turned out to be an interesting guy in that he was a hamburger guy. And he spent his life selling hamburgers, and he made a lot of money. But he really loved what we were doing, and he wanted a project. So we ended up working together with him. And he's a pretty famous guy here in America. You probably don't have these down there, but Romano's Macaroni Grill is his, and a bunch of others. He became a close family friend. He's my son's godfather. Here he is the day my son was born. And I keep this date in mind right here. It's going to come up again later. So that's the day my son was born. And Phil wrote a book. You should get this. It's quite good. It tells his life story. The other person in our story who was the real glue that kept us together from falling apart was Amalia, who was a brilliant woman who really to this day still keeps us all in line. We stay close. Still stay pretty close. And she was a good businesswoman, and she helped us navigate all the waters with Phil. So what was the problem in 1985 with getting something done? And the issue was with the FDA. So around this time, there was a valve out there called the Bjork-Shiley valve, and it ended up fracturing from metal fatigue. These metal struts here fractured. You can see one on this picture here, right there. And when that fractured, this poppet would come flying off and patients would die instantaneously. So It was the biggest liability lawsuit in the history of America back then. Pfizer had to pay out about $1 billion in penalties. And the guy that approved this valve also was in charge of approving our stent. So he wasn't excited about metal in the coronaries. But there were other people before us, and I'm just going to show you a quick bunch of these very interesting devices that were used in animals. So we weren't the first. Julio built on the work of others. And these are all animal studies with all sorts of devices, but notice they're all springs. And Julio realized that if you want something to stay in the vessel with accuracy, you have to make it balloon expandable. So here's the very first balloon expandable stent he ever made. And I'll skip that. Here's us in the lab in the early days, playing in his lab there. Now that we had Phil's money, we were able to do as many animals as we wanted. So here's the first case that Julio did. He tied the aorta off of a dog, and then he put a rubber band on it. And then he came back later and put a stent inside of it. And here's the stent 6 months later. And he was really shocked that it stayed open, but the stent was able to prop it open and resist the recoil of the rubber band. So he knew that it was strong enough to put in there. But the most important thing was that metal and tissue interface. And by looking inside the vessel, we were able to see that this whole vessel was now coated with a brand new endothelium that was functionally normal. That gave rise to the slotted tube design. And here it is in our first few cases. These are porticable shunts that we did. And wherever we put the stents, they always seem to stay open. Here's the first aneurysm. We created an aneurysm in a dog, and then we were able to place a Palmaz stent way up here with some PTFE right there. And the graft is dangling down here. We didn't anchor it. And you can see that the aneurysm was exteriorized. We were interested in pediatric applications. These are stents I put in a dog. And up here is a big 12 millimeter stent, and this one here is about a 6 millimeter tapered because the balloon was tapered. So this gave me the idea of doing pediatric cases, and we introduced, here's what the stent looked like at explantation. So I had brought this to Chuck Mullen's attention, who was a premier cardiologist in the world at the time for kids, and he was blown away by the whole thing, and he took off, and we gave him all the pediatric applications, and the rest is history. So from this idea, though, I had the idea of a TAVR. Here you can see my initial drawings. Here's a slotted tube with a valve suspended in it. And we played with this for quite some time, but I couldn't figure out the access and how to crush it and keep it small enough. And we gave up on it because we had too many other projects to work on. So I wish I had at least filed the patents, but I didn't. Here's the very first iliac stent ever placed in man by our colleagues, Gertz Richter. Notice the date. That's the day my son was born. So that's why I couldn't be there in Europe when the case was done, because we were waiting for little Brian to get born. So important date. So if you ever want to know how long stents have been around, just call my son and ask him how old he is. So that's 33 years now. So from there, we went to the small vessels, and this was the very first stent. This is the rigid stent. It was 15 millimeters in length, and this worked really good in the right coronaries. It was pretty easy to get into the circumflex and LAD in the animals. But of course, that was not diseased vessels and in perfect condition. So here's the very first animal ever done, the first coronary stent here in the LAD 6 months later, and then 13 months later. All the stents were always open in the animals. Of course, these were normal vessels, but we did have to prepare the animals to make it work. I'm going to skip this in the interest of time. One of the things that we learned, we take for granted that you just throw a stent in and nothing happens, right? Most of them stay open. But these are bare metal stents, of course. We did notice something really interesting, was quite scary. When we explanted the vessels or the stents, we noticed that they were squeaky clean at a week and 3 weeks, but then all of a sudden at 8 weeks, we saw this huge doubling and tripling of the intimal thickness right here. And I remember really getting worried about this, because the angiogram showed a little thickening, and then the histology and everything, the pathology showed a thickening. And I called Julio and I said, Julio, I think we're in trouble. I think they're all starting to close. He said, yeah, I knew it. I knew it was just too good to be true. We kept the study going, and at 32 weeks, we noticed that all the tissue finally regressed, and they looked actually better than when we put them in, almost, because there was some expansion. So that's a very important observation. And then we looked under the microscope, we were able to find out why that was. And it was really a cellular reaction to injury that regressed over time. We worried about side branches, so we looked at all the side branches with electron microscopy. We were able to see that they stayed open. We looked very carefully at the endothelium, because we knew a healthy endothelium would be the secret to success. We didn't want to have any thrombosis. And it turns out the endothelial cells are completely normal. It's not pseudo-intima. This is real true neo-endothelialization. And these are immature cells because they're polygonal, and a normal vessel will not pick up silver. So silver, by virtue of the fact that it's picked up here, tells you it's endothelium. And then we also checked the refractory-related antigen, which proves it's true endothelium. The other thing was thrombosis. So we actually did this amazing randomized trial with about 30 dogs. We did histology, and we also did indium labeling, which is an amazing study, a tremendous amount of work over a long period of time. We wanted to be absolutely sure that we had the right cocktail. So up here is a stent, a coronary stent, in an animal that received no aspirin, no persantine. That's what we used back then. We didn't have any Plavix, and did not receive heparin or anything else. This is an animal that received aspirin, persantine, and heparin. This is an animal that had aspirin, persantine, heparin, and dextran. And when we did the labeling, there was almost no platelet uptake here, some here, and a lot here. So dextran was the secret. And everyone always asks me, why did you pick dextran? Well, I spent a lot of time working on this to try and figure out what the best antiplatelet agents were at the time, and dextran turned out. And it doesn't really inhibit P2Y12. It actually works in a different manner. It prevents those platelets from clumping. But it was a remarkable advance, and it gave us some security that we're going to be okay in the coronaries if we use dextran. So that's how the dextran story started. The other thing we had to work on was mechanical issues. Normal coronaries in an animal are easy to deploy a stent. What happens when you put a stent in a diseased human vessel? So this took a lot of creativity. So we ended up taking cadaver specimens of atherosclerotic vessels, and we just throw stents in them, explanted coronaries, and just see what it looked like. But then we had this great idea of creating a xenograft. I can't find any slides from those days. For some reason, I can't. I didn't record them, I think. But we actually took human coronaries and we created a xenograft, meaning we put the human coronaries in the femoral arteries of a dog. So we resect the femoral artery in the dog and do an end-to-end anastomosis and put a human coronary in the femoral. And then we'd go in, sew it together, and then we'd go in and put a stent in there. And that's what these cases are. These are human coronaries, xenografts in an animal. And here's a stent showing that it tacks up the wall. And if you look closely, it looks like there's thumbtacks tacking up some wallpaper. So that was to prove to the FDA that you could actually do that in a human coronary. And it was important we did this study because they did ask for that in the time. We had to work on metals. We ended up with 316L. This is an example. We used gold, we used tantalum. This happens to be a tantalum stent in a coronary, and very radiopaque, but had some other properties that weren't as good. And once we had Phil's money, we did everything. So we were putting stents everywhere. This is just one of the countless renals that we did to prove that you could nail it in the ostium. So by 1987, we were ready to do our first human. And I won't go through this in great detail, except to mention that it was done from a Sones technique using a 9 French guide, and right coronaries only were done with collaterals and stable angina. So that was the type of patient that we were doing. We knew the stent wouldn't go through the guide very easily, so we actually backloaded it into the stent. I don't have time to explain that, how we did that, but it worked every time. So back then, all we had was aspirin, persantine, Antarein, all antiplatelet agents, and then dextran. And we sent them home in 24 hours. There's no Coumadin, and off they went. Here's the very first case, December 1987 in Sao Paulo, Brazil. And here's me and Julio right here. Here's Dr. Eduardo de Souza, the first patient. And here's the case we did. It was ended up being a total occlusion. He had good collateral, so we didn't have an infarct. And so we wired it, put a stent in there, and then 6 months later it was open. And 13 years later, he had a follow-up and it was still open. Some restenosis in there, but he was asymptomatic. Here's a second case I did. This was done in the US in March of 1988, and it started out as a tight lesion in the right, but we ballooned it and yet we had a total occlusion. And so thankfully, we had 4 stents in our possession that we brought from J&J. And I ballooned it and it looked like it was exactly 60 millimeters. So we put the 4 stents in. Here it is as we're chipping away at it, and there's the final result. So we got in a lot of trouble for this because we weren't supposed to do that, but we had the stents and we did it. So over time, we were able to get some human explants to see what the stents looked like in humans. And here's an example of a right coronary stent. The ostium is over here. And you see the plaques pushed away and a brand new endothelium inside, just like we expected. So this was primary evidence that the stents acted just like they did in animals, despite the presence of plaque. One of the interesting findings here is that the stent has been in the patient for 2 years, and it's bent because the guiding catheter probably bent it. And of course, it was still open, but of course, it's not really endothelialized because it's not touching the tissue. So we learned from this that in order for the endothelium to really be properly laid down, it has to be up against the wall. That's why we encouraged getting the stents as large as possible and making sure that the stents were completely embedded in the wall. Here's another stent that was 2 years old, and a patient who died of a pulmonary embolus. But you can see two stents there overlapped. Really great result. So despite the early success, by 1989, we opened this up to the world, and then everything went wrong. So when I was doing all the cases, everything was done very slowly, methodically, and we did everything by the book. But when we opened it up worldwide, we lost control of everything. And the issues we ended up with the stent was obviously rigid. The doctors had trouble getting it down vessels. The stent was coming off the balloons because we didn't have a dedicated balloon. We were just taking balloons off the shelf. We had a lot more thrombosis than I'd like to see. I never had a stent clot, symptomatic clot. I had one clot without symptoms. But once we opened it up to the multiple centers, we saw about a 5% thrombosis rate, which was too high. And a lot of that was from underdilatation of the stent. We had a lot of bleeding because these were all femoral cases, and the doctors didn't want to stop the heparin, so they were pulling sheets on heparin. So a lot of issues. Then, of course, restenosis looked like it was going to be about 20 or 30%. I'm going to skip that. And it was very hard to get the doctors to overdilate the stent. After I looked at all the films, I realized that people were so embedded with the idea of angioplasty, don't overdo it, don't get a dissection, don't tear the vessel. Well, in order to get a stent to work, you've got to overdilate it. And that was a fundamental problem, that doctors just didn't really feel comfortable overdilating the stent. And we use the term, make sure the stent is the biggest thing in the artery. It should look like a snake that ate a rabbit. That's what a stent should look like. And when you looked at all the cases, nobody was doing that. So it was really hard to convince people. That was later codified when Colombo turned the tide here in 1985. You can see with IVUS and getting the stent as big as possible and ticolet and overdilating. So even though I want everybody to do that, not everybody was willing to do it, but Colombo did a real methodical study with IVUS and showed that the thrombosis rate could get down to 1%. So by 1988, we had an experience in the U.S., but our thrombosis rate was too high, and we couldn't get the investigators to overdilate. So we added warfarin, and that's how we started with Coumadin. And it wasn't the plan, but it's what we had to do to get everybody on board. And it created a real problem because the patients were in the hospital for a week. You had to transition from heparin to warfarin, and the bleeding results were really, really bad. So that was an unfortunate, I think, unforced error. So another surgeon looked at our results now and said, why do you want a stent? A stent is like a time bomb waiting to explode in your chest. So deliverability was a problem, and I came up with the idea of a flexible segments. By one day we're at the airport, and I was looking at these boxcars going by, and every place you look, there was boxcars, right? So I came up with this idea of a flexible stent with 3 segments in the spiral in the middle, and we showed it to J&J, and they liked it. They said, we can't do that. You know, we make the stent with EDM, and we can't do anything but rectangles. So anyway, make a long story short, we ended up with the Palmaz-Schatz stent. Here's the very first case ever done, proximal lesion here, and 6 months later. We had a guide liner to try and help it keep it on, the very first guide liner, you see it here, and that worked pretty good, but it was still a little bit too much, very difficult to work with. The stress trial everybody knows about. We showed the stress and Benestent trial that stents did a little bit better than angioplasty, enough to get approved. And we got approved in the US, and we started moving into other iterations of it. Here's the Crown Palmaz-Schatz stent, which was our attempt to make it a little more flexible, and the velocity. This then became the Cypher stent. The media wasn't very cooperative. They're always looking for bad news, and hear a bunch of bad news reports from the media. I don't have time to go through them all, but it was not good. They called them treatment traps, tiny time bombs, in cold blood. Stents were clotting like crazy. This was really misrepresented, and this was from the Swedish study. So only those tiny time bombs, they were called. So this was a result of the ESC 2006 where the Swedes came out and said that there were people dying of the drug-coated stent, and they had it all wrong. They came out later and said they had it wrong, and they kind of apologized. So, and there's a study from Rotterdam where they looked at 18,000 patients, and they said, look, drug-coated stents do not clot more than bare metal stents. So that kind of put an end to it finally. And then, of course, the most famous stent in the world of Mother Teresa. There's our young and beautiful Dr. Aubanel and the Scripps team behind her. So she'll have to tell you that story on her own. It was probably the funniest 3 weeks of all of our lives. Don't you agree? And of course, we got a lot of press about it. So I'm going to skip that in the interest of time. I'll tell you about what happened with the FDA. We tried to get it approved in 1993. And in 1993, the FDA approved all these products without randomized trials. You see them here, but they rejected the Palmaz-Schatz stent. So it was a little paradox there. But in the end, we got approved in 1984. Other stents started coming out pretty quickly. You had the wall stent, self-expanding, and all these other balloon expandable stents, and the bioabsorbable stent, of course. And here's the wall stent. This came out in Europe. They treated a bunch of patients, but the thrombosis rate was very high, pushing 25%. And so that disappeared pretty quickly. The Gianturco and Rubin stent, first stent approved in the US, and 93, 94, I think. And that disappeared pretty quickly. That lasted about a year. This is the AVE micro stent, and became the GFX stent later on from Medtronic, and now officially is the Onyx stent. It's basically the Onyx stent with a couple of revisions. Multi-Link had quite a bit of success. This is now the Zion stent, drug-coated. These stents kind of disappeared, and within 10 years, look at all the competitors that were out there in Europe. There were a lot of procedures that were coming out as well. These all disappeared. DCA, tech, lasers all disappeared. Kenzie catheter, rotablator is still around, of course, in 5% of the patients. Just a quick word about the patents. Everyone always asks about this, and we had 6 patents. Those last 3 are mine here, and these 3 are Julio's. And why this is important is that here's the spiral stent right there from 1992. We never made that because we couldn't make the curve. So we ended up with the 984 patent. Why that's important is that this is the patent that ruled the day in the courts, and we did 10 years of litigation with all the companies that told us it would never work, and all the companies that said that that theirs were different than ours. We sued them all for patent infringement, and we were able to win the day. And this one slide summarizes how we won. The lawyers convinced the jury that all these slides have slots and half slots, and in green are all the repeating elements, and all of the other stents have all of this with flexible connectors. The only difference is theirs is round and these are rectangles. So with that, the jury agreed with us. And after many years of litigation, Judge Robinson in Delaware ruled in our favor and said it was time to give Dr. Palmaz his due and bring the litigation to a close. So in the end, J&J won. They collected over $3 billion in penalties from all the companies that were copying us. I don't have time to go through all this. I will mention a couple things, though, that we're real proud of. One is we ended up in the Smithsonian permanent exhibit there in the Inventors Hall of Fame, and in there you'll see an exhibit called the Inventing in America, and there's the Palmaz stent. There's a Palmaz-Schatz stent in there somewhere. They rotate them around, but they wanted all of our stuff, so we sent them all our prototypes and everything. But we're sitting right in the middle of this exhibit, and on one side is Irwin Jacobs' first cell phone, and on the other side is Steve Jobs' first computer. So pretty good company. And of course, last year we won the Rusk Prize, which is the National Academy of Engineering. It's the American Nobel Prize for Biomedical Engineering, and recognized with John Simpson and Paul Yock. And it's the first time we've been recognized together. So that was a real honor. So in summary, where are we after all these years? Well, stents are here to stay. It's hard to believe. And I don't think anything's going to replace them. Drug delivery is going to become more effective, safer. Bioabsorbable stents are gone. They're not going to come back, I don't think. Polymers have already gone away, and these other new stents are out. They're not. We're trying to figure out where they fit in. These two don't really work that well, in my opinion. This one tends to embolize. This one we're going to try out pretty soon with nano surface stent that we're going to give a try. But you don't see too many other products coming out. But in a final statement, a few medical devices or products have stood with the test of time, been applied to more patients with such a profound impact on morbidity and mortality as stents. Over 100 million patients treated. Nothing's replaced them in 30 years, and nothing likely will. I'll just finish with this one slide. I always have to mention that I'm the only one of the trio that doesn't have a stent. Both Julio and Phil ended up having angina, little end STEMIs, and ended up with stents. So here's the three of us. We just got together for the first time in many years, and we got a little older, but we're still standing. And I'm just waiting for my stent. I'll have to call Patricia and tell her to put it in for me. I'll come down there and see it. But so far, so good. So with that, I'll close. And thank you very much for your attention, and thank you, Pat, for letting me talk to you today about this.
Great story, Richard. It's unbelievable. It's so incredible that what you had to go through and what one inventor has to go through to fulfill a dream. And you accomplished it, so you're a big winner. And congratulations that you have seen it in life and had enjoyed it in life. And you've seen the results of all the human good that you have done. There's several questions.
Great story.
Yes, great story. We have several questions from audience and from people that would like to know. And so how come this is not accessible to all people that need it? What can we do to make it available for all? What are we doing to do this?
Well, I'm not sure what you mean by that. You mean in like the maybe rural communities or where people, well, of course you have to have a cath lab and no lab, no stent, right? So certainly pricing is not as much of an issue anymore. That was a barrier. You probably remember the early days, they were very expensive. Stents were super expensive. But with competition, that's come down. I think awareness, I think the bigger question is making sure that patients know when to come to the hospital. You always hate to hear the patient who's been having stuttering chest pain who won't come into the hospital. We're seeing that now with COVID. I don't know what it's like down there, but patients don't want to come to the hospital. But you have to have a cath lab, of course, if you want to deliver the service, and not everybody has that. We get a lot of patients from El Centro, and there's no cath lab out there, so they, especially for the emergencies, the STEMIs, they have to air vac them. It's a big deal, very expensive, and that actually speaks to your question. And if you don't have a lab, then you have to have an air-vac system. And I'm really surprised how easy it is for us to get patients from these rural areas to us. They'll come by helicopter and by airplane just a couple hours away, and they'll find their way to the lab. But of course, they get lytics and all that. So, good question.
Yes, in Mexico tenemos como 200,000 muertes por infarto agudo del miocardio al año. Y solo la mitad de la gente tiene acceso a angioplastía, y sí estamos trabajando para poder hacer esto una posibilidad con el código infarto, trabajando en consenso con el gobierno de México para lograrlo. We're trying to get access to these technologies for all people in Mexico by creating the infarct code that we are doing to get it all to all the rural areas and to everyone. We hope we can accomplish it with the government. Hay más preguntas. Sigue siendo la diabetes, diabetes is the number one cause of coronary disease and obstruction, and stents are a solution for this as well.
Yeah, they don't work as good. Everyone knows the data about that. Just like bypasses don't work that great in diabetic patients, and it's a real issue. Some of the companies had claims that it works better than other stents in diabetes. I think they're all very equal, and I don't know what your favorite stent is, but I tend to use a lot of Onyx. And all the studies do suggest that the diabetics, especially the really bad diabetics, have a higher restenosis rate, higher complication rate. So I don't think we have a stent that's dedicated for that works better than the others. So I think the three major stents that we use are probably very comparable. So it doesn't really come into play. The bigger question is whether those patients should get bypassed if they have three vessel disease, and that's still arguable.
No, la realidad de los diabéticos es que tienen que modificar sus formas de comer, ejercicio, si no quieren tener un infarto, porque esta es la enfermedad que ataca principalmente a los diabéticos. Tenemos que trabajar en una cultura de comer correctamente, balanceado, hacer ejercicio y de no fumar. Eso es definitivo para tener una vida sana y llegar a una vejez feliz. Hay unas preguntas. There's some questions from the audience that probably more so from our people are curious to know what you think about Tijuana. And you have something that want to tell us about your experience in Tijuana when you have come, if you like it, what you think of Tijuana, and you think Tijuana Innovadora is a good forum for people.
That's a great question. I was down there to see Patricia, I don't know, a few years ago, and I met so many nice people there. And what I learned was, and since learned, is what a vibrant community you have there. And since I don't know my way around that much, the few times I've gone down there and I've been there with the local people who can show me around, I was very impressed, very, very impressed with just the social atmosphere, the cultural atmosphere. The restaurants were fantastic. And it was quite a surprise because we don't really go down there very much, but the few times that I went down, I was really, really surprised. I've actually brought some guests down there when I have some people from out of town to see the community down there. It's really exceptional. And the hospital there was great. I spent a lot of time with Patricia and some of the other doctors looking at that was the stem cell meeting that we had down there, and really, really impressed with the good work that you're doing down there. Great little community.
Esperamos que Richard regrese con nosotros y próximamente esperemos que la pandemia logramos vencerla y podamos regresar a la investigación y a descubrimientos como los que ha hecho Richard Schatz para seguir ofreciendo salud y vida para nuestros pacientes. Richard, thank you so much for being with us, and I thank you as usual, my great friend and my mentor, Richard. Thank you, and I hope to see you soon in Tijuana.
It's a real pleasure, Pat, and congratulations on all the good work you're doing down there. Adios.
Adios.